In this last video in this unit on acyl transfer reactions, we're going to consider the concept of thioesters. And again, this is trying to get us into the biochemical applications of these reactions. And it turns out that thioesters are one of the main mechanisms by which cells can activate carboxylic acids. Okay, so carboxylic acids are ubiquitous in your body. There are carboxylic acids present just about at every stage in metabolism. They're involved in fat breakdown, they're involved in the citric acid cycle, they're also involved as various small molecule messengers in the body. So your body definitely uses these things and has to do chemical reactions with these things. But if you've been able to take something out of this unit so far, you should realize we have not looked very much at the reactions of carboxylic acids. We've looked a lot at the reactions of carboxylic acid derivatives, the acyl transfer mechanism and the hydrolysis mechanism, but we have not really looked at carboxylic acids themselves. And there's a good reason for that. That is that carboxylic acids do not generally participate in acyl transfer reactions the way that carboxylic acid derivatives do. In fact, the only reaction of a carboxylic acid itself that we have studied is the Fischer esterification, in which you take a carboxylic acid and convert it into an ester. But if you think back to that reaction has to take place under strongly acidic conditions, and in fact it needs to take place in the absence, or at least in a minimal amount of water, because water would actually take the ester and hydrolyze it back by the same mechanism. It is clear that Fischer esterification is not going to be taking place in living cells. So let's think about the carboxylic acid derivatives and think about what does happen inside of cells. Well, first of all, the most reactive carboxylic acid derivatives, namely the acid chlorides and the anhydrides, are too reactive to exist in the aqueous environment of the cell. They will be hydrolyzed too readily. But cells contain plenty of esters, especially acetate esters, those are actually quite common, and amides, as we have already seen. So how do they make these functional groups? Well, the answer, as you might have guessed from the title of this lesson, is to use thioesters, which are the sulfur analog of esters. Okay, so a diagram of a thioester is here. The only difference between a thioester and a regular ester is that we have a sulfur atom in the chain instead of an oxygen atom. You still have a carbon-oxygen double bond. That carbonyl group remains and is not changed into a sulfur. Okay, so why are thioesters good? Well, the answer is that they hydrolyze at about the same rate as oxygen esters. So we said anhydrides and acid chlorides hydrolyze too quickly. Esters are stable in the cellular environment. So because thioesters do not hydrolyze any faster, they will be just as stable as regular esters are. But their reactivity towards nitrogen, carbon, and even some other oxygen nucleophiles is more similar to that of anhydrides than esters. So they can be used as starting materials for the synthesis of esters and amides. Why? Well, like many other things in organic chemistry, we can fundamentally trace the answer back to the pKa table. So earlier in this unit, we've looked at the fact that what makes acid chlorides the most reactive is that the leaving group that is expelled in the acyl transfer mechanism is Cl-, which is the weakest base. Anhydrides are the next most reactive because they expel the next weakest base. So the leaving group that is expelled when a thioester participates in an acyl transfer reaction is a thiolate anion. The thiolate is the conjugate base of a thiol. Again, all of these are labeled in the diagram on the bottom if you are unfamiliar with this terminology. A thiol is the sulfur equivalent of an alcohol. A thiolate is the sulfur equivalent of an alkoxide. But a thiolate is a much weaker base than an alkoxide is, because to know how strong a base is, you've got to look at the pKa of the conjugate acid. An alcohol has a pKa of 16, whereas a thiol has a pKa of 10.5, because the thiol is much more acidic. The thiolate is a weaker base. So let's look at an example of how this is put into practice. Anyone who is watching this who's taken a biology course has probably at least seen the name acetyl-CoA. May have no idea whatsoever what the structure is, and we're going to look at that here. But fundamentally, acetyl-CoA is the biological equivalent of acetic anhydride, in that it serves as an acetylating agent. So depicted on the left here is coenzyme A. Coenzymes are different molecules that react together with enzymes to carry out reactions that are important inside the cell. As you can see, coenzyme A is quite large. It's got an adenine, it's got a ribose ring, it's got 2 phosphates. These are things that might be familiar to you if you've been watching the last several videos. Then you have this linker here with a couple of amides in it, an OH, some carbons, but then the business end of coenzyme A is the thiol, the SH, all the way over at the left-hand end of it. So if coenzyme A gets acetylated, and we're not going to consider exactly how that happens in this particular video, you have acetyl coenzyme A. You might have met acetyl coenzyme A as what is fed into the citric acid cycle. So acetyl coenzyme A reacts with oxaloacetate to make citrate. Acetyl coenzyme A is also present in the metabolism of fatty acids. So I'm just going to give you one example of how acetyl coenzyme A is used as an acetylating agent in the body, and that is in the biosynthesis of the neurotransmitter acetylcholine. So I am actually abbreviating acetyl coenzyme A with the acetyl group followed by S-CoA. Okay? The reason why, incidentally, why coenzyme A needs to be so large is being a coenzyme, it is involved in enzymatic reactions. And the adenine, the ribose, the phosphates, and all these other groups are designed to fit into a particular pocket in the enzyme that will tell the enzyme, okay, I've got active molecule in here, it's time to catalyze a reaction. Frequently, that will cause a conformational change in the enzyme. So we have our acetyl-CoA, and what we're going to start with is a molecule called choline. And choline, as you can see, has a quaternary ammonium group on one end, but then it has a free OH group on the other end. So it is nucleophilic, it has the oxygen there, and it's got the hydrogen that can be lost. So this serves as a nucleophile. It's going to attack the carbonyl carbon just like any other acyl transfer mechanism, except this one, of course, has to be enzyme catalyzed, and then free coenzyme A is kicked off as a leaving group. Initially, it's going to be kicked off as the anion, but then in the course of the reaction, everything is going to get protonated so that it ends up neutral. So again, this is just one example. This just gives you a flavor for how acetyl coenzyme A works, but it is important to note that it is a thioester, and that thioesters are the compounds that are very frequently used in the body as starting materials in acyl transfer reactions.